Hello, I am Matthew Godat, and welcome to my Lab 3 video. So our introduction, the purpose of this lab is to use Newton's laws and some random initial conditions to calculate the mass of a black hole. And then we change the system to that of a planet and its moon, and then determine the initial velocity that allows our ship to be affected by both the planet and the moon while not crashing into them. And we're going to be using the principles of Newton's second law and then universal gravitation. Um, our final discoveries will show that the black hole has a mass of 1.01782 times 10 to the 34, and that the initial velocity of negative 13 times 10 to the 3 and 15 times 10 to the 3 is 0 provide the correct initial velocities for no collisions. Beginning with the code for part 1, where we are trying to find the mass of the black hole, we define our system as the star and the surroundings as the black hole. A random seed is entered based on our Georgia Tech email to give us a trajectory, and then from here we input the initial conditions of the star mass, which is given, and then the gravitational constant, which is given. In order to find the mass of the black hole, we first need to apply Newton's second laws, finding the gravitational force, and extract the mass from this. So first we need to calculate F net, which we do by setting F net equal to the change in momentum. And then we extract the perpendicular and parallel components from this, and then use this formula here, which is just the gravitational formula rearranged to calculate the mass. The results from this code show that our mass is equal to 1.01782 times 10 to the 34. And here I've attached two screenshots from different points in the code's runtime. This one shows that midway through you can see the difference in forces between these two, and then over here that we have the final calculation of the mass of the black hole. Moving on to the second part of the lab, we start by redefining our system and surroundings. So our system becomes that of the ship, and the surroundings become that of the planet and the moon. And there's a variety of forces that we need to calculate in this second part of the lab. The first is the force on the moon, which comes from the planet and is the cause of the moon's orbit, and that's calculated here. We also have to calculate the gravitational force on the spaceship, which is also in orbit, but is affected by the forces of both the moon and the planet. So that calculation is done here. From here, we just have to update the velocity and position, and then check for collisions. In order to find an initial velocity for the ship that allowed it to show that it was being affected by both the forces of the planet and the moon, I just used a simple guess and check method, and I came up with that the ship speed in the x direction needs to be negative 13 times 10 to the 3, and the ship speed in the y direction is 15 times 10 to the 3. The results of this code are shown in the screenshot to the right. You can see that we have a non-constant orbit of our ship, which is labeled in this magenta line, where at different points in its orbit, it's being more affected by the gravitational pull of the moon rather than the planet. And sources of error, we were instructed to find a figure 8 orbit, but I could not obtain this. And this is likely due to my own lack of guess and check ability, and I can't sit here for hours and hours and try to get that. Finally, moving on to the questions. What does it mean? What is the difference between net force and the rate of change in momentum? Well, while these two concepts are really closely related and can sometimes even be said equal to each other, the net force is the sum of all forces acting on an object, and the rate of change of momentum is how quickly the momentum changes over time. The net force causes this change in momentum, and the change in momentum describes how the momentum is changing. And what if we want to predict the motion of the entire system? Well, because of their relatively small mass compared to the black hole and the star, we could likely neglect the mass of the planet and ship when predicting the motion of the entire system. They're just so small compared to the huge black hole that they don't change its momentum in any significant way. Thank you all for listening. I hope my Lab 3 brightened your day.